All right, guys, it's time. It's that time of. It's that time again. We're gonna do exam 3 for Physics 206 from 2019. Um, all right. So, as we all know, the first question on this exam is gonna be deriving the expressions for IR and I theta. So, this isn't too complicated, um, in most cases. So, what we want to start off with is that's big. IR equals uh, cosine theta I plus sine theta j. I might even post this separately just because it's such an important question, I guess. And then I theta is negative sine theta I plus cosine theta j. Okay, now our first step is taking the derivatives of these two things, right? Okay, so what we want to do is do di, dr, dt. Yeah, and then so what we're going to do that is by taking the derivative with respect to theta, it's the same sort of thing of these things, which we can then say is like doing d theta dt times d over, d over d theta of cosine theta I plus sine theta j. And that equals negative sine theta I plus cosine theta j times, actually, let me move this down so we have space. Let me move this over here. Oh, Lord. We're having problems today. Okay. Alright, doesn't want to work. Okay, so we're just going to go down here. So we're going to have d theta dt times whatever the derivative of that would be. So negative sine theta I plus cosine theta j. And so we end up having that d theta dt is multiplied by I theta for that one. So di dr dt equals that. Now for di theta dt, we're going to have that di theta dt times d theta dt equals d theta dt times d theta. And then that's going to be negative sine theta plus cosine theta j. And we're going to end up having d theta dt times, this ends up being negative cosine theta I minus sine theta j. And then we have that di theta dt equals negative d theta dt negative IR. So those are our derivatives there. Perfect. Okay, we'll use those in a second. And then, that was embarrassing. All right, so let's see here. We have we're going to take the derivative of the position, Ri, right? And so the way that's going to work is velocity is going to be the derivative of position. And so we have dr dt IR, plus r dir dt. And then that's going to end up being dr dt IR plus r d theta dt I theta, which we can also say is dr dt IR plus r alpha, or sorry, r omega I theta. So that's going to be our velocity. And then we take back acceleration. Acceleration is the derivative of velocity. And so we have that, we're going to take the derivative of dr dt, ir plus r d theta dt I theta. So we're going to have a couple terms here. So we're going to have d squared r dt squared, so they're going to do dr ir plus dr dt di or dr dir dt plus dr dt d theta dt I theta plus r d squared, or the second derivative of theta, so the derivative of omega, and then I theta plus r d theta dt d I theta dt. Okay, and we're just distributing this to every term using the product rule. Okay, and then we end up having that acceleration equals d squared r dt squared ir plus and dr or dr dt is d theta dt, so we can say dr dt d theta dt I theta plus dr dt d theta dt I theta, and then plus r, actually this is alpha, r d squared theta dt squared I theta plus, or minus r d theta dt times di theta dt, which is that. So this would be squared. Or, wait a minute. One second. Yeah, this is the same thing. Sorry, d theta dt IR. Okay, so then we can just group these together. We get d squared r dt squared minus r d theta dt squared IR plus 2 dr dt d theta dt plus r d squared theta dt squared I theta. Okay. And then we can also just write this as d squared r dt squared minus r omega squared IR plus 2 dr dt omega plus r alpha I theta. And so there we go. We've got our acceleration and we've got our velocity. Cool. All right, so that's our answers here. There we go. Okay. Now, moving on. All right, so another galaxy far, far away, a small moon of mass m travels in a circle of radius r about the fixed sun. The force exerted by the sun on the moon is not a usual force of gravity. It's attractive and has the magnitude here. Okay. So we see that it's an attractive force, and it's not the usual force of gravity. Okay, so cool. So C and R are constants, and okay. So find the total kinetic energy, or find the total energy, kinetic, and potential for the moon as a function of R. Okay, so we're going to use the law of conservation of energy, or not conservation of energy, but just energy. Remember that that's U, and then we have K equals 1/2 mv squared. Okay, cool. So let's see here. What we want to do first is we could just right off the bat. Well, actually, let's think about this, Rick. So we have our sun here, and we have this moon going around it, and it's being drawn in by this force. So it's got this radial. Let's just draw our coordinate system here. IR. Cool. Okay. So we know we just say it's moving in that direction. So since the force is attractive, it's towards the sun. That way, that means it's negative, or it's pointing in the negative direction. So when we can right off the bat find the potential energy. So take the negative of the force, right? Okay, so we add 1, divide by that number. So we have those two negatives would cancel out, and then we'd have a negative from the exponent. So we have negative 1/3 times Cm over R cubed. So that's our potential energy. Our kinetic energy is a little bit different. So we need to use velocity here. If you remember, we just did that. We have velocities dr dt, IR plus R, R omega I theta. Okay, cool. And we know that kinetic energy equals 1/2 mv squared, right? So let's see. Sorry. Okay. So we know that R is constant. So R equals R, so that means the derivatives of R are going to be 0. Right? So that means that's going to be 0. We wanted to find a value for omega here, because we can't leave omega, so we need a value for omega. Because right now we could do 1/2 m times dr dt IR plus R omega, but since we know that, oh, my bad, sorry. We need the magnitude of this velocity, which in our case is just going to be R omega squared, because dr dt is 0. Okay, so we know that. So then we can take this, and we have that kinetic energy is going to equal 1/2 m times R omega squared. So we need a value for omega. The way we can do that is we know that the force is only in the radial direction, so there is no force in the tangential direction, so we can say that S of theta equals 0. We can say, and then we can just set that equal to m times the radial component of acceleration, which if we remember up here is this, And since dr dt would be 0 in this problem, we can just set that equal to r alpha, m r alpha. Right? So we know that then the radius, or r alpha, or m r alpha is going to equal m r alpha is going to equal 0, so that means alpha is going to be 0 because the mass and the radius aren't 0. So we know alpha is 0, but then we also can say, we can also set the force equal to the radial component of acceleration L as well. So again, that's going to be 0. This component is going to be 0. Part of this is going to be 0. So we can say negative m r omega squared equals what we were given in the problem, which would be this. And since it's the negative direction, we have negative cm r to the 4th power. Okay. Then we cancel out these m's and this negative, and so that means we have that omega squared equals c over r to the 5th. And since we have a value for omega squared here, r squared omega squared, we plug that in. So we have that it's 1/2 m r squared times c squared over r to the 5th, which is going to just equal 1/2 m c squared over r cubed. Right? Okay. Cool. And then we know, then we just add that together to get energy. Kinetic plus potential. So we get 1/2 m c squared over, or not c squared, sorry. C over r to the 3rd power minus cm 3r cubed. Okay, so that's our answer. Yes. Okay, cool. Now moving on. A massless horizontal rod of length 2s is free to rotate about a vertical axis as shown. Okay, so free to rotate means that there's no external torque. That's good. This is going to most likely be a angular moment, conservation of angular momentum problem. So object 1, it has 2 small objects on the rod. So object 1 has a mass m1 and is fixed at the end of a rod. Object 2 has mass m2 and is at rest next to the axle. The axle is given an angular velocity omega naught. At a time defined to be t equals 0, object 2 begins to move along the rod so that its distance from the axle is given by ct, where c is known constant. A, what will be the angular velocity of the rod as a function of time? What will be the angular velocity of the rod at the instance when the object 2 reaches the end of the rod? And if object 2 leaves the rod, when it reaches the end with the velocity of magnitude vf parallel to the rod, what will be the angular velocity of the rod after the object leaves? Okay. So a lot going on in this question here. But there's nothing we can't look at. Okay, so we have these 2 objects here. So part A is asking what will be the angular velocity of the rod as a function of time. Okay, so we know that angular velocity equals r cross, angular velocity equals r cross p, right? So r cross p, it also equals r m v theta k direction plus or also equals r m omega squared. So that's what we're going to use, is that. So L initial equals L final. Okay, so part A is asking what will be the angular velocity of the rod as a function of time. Okay, so we know that when the axle is given an angular velocity omega naught. Okay. Okay, so first we have that we're not given an inertia, So we just have that m1 squared, or m1, the mass, the first mass on the end here, right here, is gonna have a angular momentum of Rm. It's a distance s away from the center, so s squared omega naught squared, or not omega naught squared. Okay, perfect. Would the second mass have one as well? No, it wouldn't. Okay, so then we have mass 1 now has still a distance s squared away, but now has a new angular momentum of W, plus m2. Oh, and the reason we won't have m2 on this side is because its distance from the axis is 0, right? Because it's right next to it. So that's just going to go to 0. Okay, so then we also have, now when it starts moving and m2 starts moving away from the rod, it's going to have a distance of c1t squared, or ct. ct squared omega. Cool. And so part A is asking for the angular velocity at the instant. What is the angular velocity of the rod as a function of time? Okay, so then we just solve for angular velocity of the rod, which would be this new angular momentum. So we do m1 s squared omega naught over m1 s squared plus m2 c squared t2 squared, and that equals omega. Okay. Part B is asking, what will the angular velocity of the rod be at the instance when object 2 reaches the end of the rod? And so what we can do for this question is we can just say CT is the rate at which the rod, mass 2 moves along the rod. And so we know that the rod is a length s, and so this mass is going to be having to move a length of s away to the edge of the rod. And so at this point s is where that's whatever time it is once CT equals s, is where we'll have, is the time at which mass 2 will have left the rod, or like the second before, or the instance before it leaves the rod. So all we need to do is plug that into this formula here. And so we have that m1 s squared omega naught over m1 s squared plus m2 c squared times s over c squared. Yeah. And so those two c's would cancel out, and we would end up having m1 s squared omega naught over m s squared plus m2 s squared. Okay, cool. And I guess you could cancel out the s squares as well if you wanted to. Okay, part C. Part C is asking, what if object 2 leaves the rod when it reaches the end with a velocity of magnitude vf parallel to the rod, what will be the angular velocity of the rod after the object leaves? Okay, so this is the top view, and so we have that the rod is moving in this radial direction, or tangential direction, and then we have a radial direction out, and then K would be towards us, or the Z direction would be towards us, or the Z axis would be up towards our face coming out of the page. And so, cool, all right. So we're going to be using this version of angular momentum here to calculate this one. So we're going to have that, again, m1s squared omega naught equals m1s squared times the new angular momentum when it's when the second object leaves the rod, plus the second object's mass times s squared, or, well, let me see here. Be 0. Oh yeah, it would just be 0 because it's left the rod. It's no longer on it anymore. It leaving the rod will change the angular momentum itself. Okay. Times VF. Or we could really just say, if we want to use that version still, we have 0 times VF. Okay. So that goes to 0. Awesome. And so that means we have that angular momentum would be m1s squared omega naught over m1 s squared omega, or sorry, and so those would cancel out, and we'd end up having that omega equals omega naught for part C. Cool. Nice. All right, so the next question here is a pulley question. So a block of mass m, excuse me, well, my sneezes are on the internet now. Okay, so a block of mass m is suspended by a massless, unstretchable rope from the pulley as shown. The pulley rotates freely about a fixed horizontal axle. The rope moves around the pulley without slipping. Okay, so the pulley has a moment of inertia about its center I and a radius r. A constant force of magnitude p is applied to the pulley as shown at the known angle phi. Will be the acceleration of the block, assuming it moves down. Okay, so the hanging mass is released from rest at time equals 0. What will be the angular velocity of the pulley as a function of time? Okay, so we have part A, and we have part B. Okay, cool. So what we want to do here is make our free body diagrams. So we have our pulley. It's going to have this force phi, P on it, and it's going to have this tension force pulling down. And then I guess you could also say it has a normal force that we're not going to use in this direction. And then gravity acting down on it, technically. Okay, cool. And then we have the block. Oh, then I guess we could do our coordinate system here. We can say that, again, the counterclockwise direction is plus x in most cases. Yeah. And then we have IR out. Sorry, it's acting up. We have IR. We have IR out here. Oh my God. Okay, there we go. Jeez. This iPad's old, so bear with me for a second. Come on now. There we go. Now it wants to do its job. Okay, so we have IR, and then we have I theta. And it's really not wanting to work with me right now. Good Lord. I don't want to have to redo this whole video. What is happening? Okay. I'm just going to leave it like this. Okay, so you have IR, and then we have I theta, and then we have, I guess you could say, K coming out of the page. Right, okay. Well, actually, no. IR would be going down here, and then the radial, the tangential direction would be going down because the mass is going down. Right, okay. So then we have K would be into the page. Okay, so and then we have our block. That's horrible. All right, we have our block of mass M, and it's going to be moving down, and then it's going to have the tension force up. And then we'll just make this the plus y direction for that. That makes sense. Okay, cool. So we have our free body diagrams. So what we want to do now is when the block moves some distance s, so is the pulley in this direction, right? So cool. So we have that the pulley, the forces acting on the pulley are going to be, and it has a moment of inertia I about the center and a radius r. Okay, so just draw that real quick. Radius r. Okay. So the tension force is going to be acting in the opposite direction, and P is going to be working in that direction. So we have that we're going to have negative RT plus, and we can decompose that force P real quick, and it has angle phi. So we're going to use this side, which is cosine. So we're going to have P cosine phi. So plus P cosine phi because it's moving in the positive direction, because P is pushing on it in the positive x direction. Okay. Sorry, it's going to be P times R, or as you can say, R times P cosine of phi in the positive x direction. And that's going to equal its moment of inertia times alpha, some value alpha. Okay, so that's the pulleys. And then the box is going to be moving positive G minus tension equals MAY. And we can go ahead and say we have our identity that acceleration equals radius times alpha. So alpha equals acceleration divided by r. We go and just get rid of that AY, just make it A. Okay, so we're going to exchange that alpha out for acceleration, because that's what we're solving for in part A. I times A over R. And then we have mg minus t equals ma. Or sorry, I have these signs all backwards. I just noticed that because we want the tension forces to cancel out in these problems. So that means this would be negative, that would be negative. Okay, cool. My bad. Okay, so then we have mass times AY, or times A. Okay, so now we can add these two together, or we can divide R actually over to the side here. So R squared. And then mg minus t equals ma. So we can add them together. So we end up getting that the t's cancel out. And so we have mg minus p cosine of phi equals ma plus I, or inertia, a over r squared. Okay. Cool. So now we have that a would equal mg minus p cosine of phi over m plus inertia divided by r squared. Yep. Okay, cool. That's what we want for part A. Part B is asking that if the hanging mass is released from rest at t equals 0, what will be the angular velocity of the pulley as a function of time? Okay, so we know that we have acceleration equals r alpha, and we know that the derivative, or the integral of alpha, equals angular velocity, which is what we want. So we have, we're going to substitute. So then we have that the integral of a over r dt is equal to a over r, so we can just plug in what we have for a from part A, minus p cosine of phi over m plus, or really rm, because we're multiplying that to the bottom there, times the inertia over r times t, plus t naught, but that's 0 because it was released from rest at t equals 0. So that is the answer to part B. So we have that part A is a equals mg minus p cosine of phi over m plus, okay, that was a bad box, okay, there's a box, and then we have that alpha, or angular velocity equals mg minus p cosine of phi over rm minus, or plus that. Okay, cool. Times t. All right. Yeah, this third exam is definitely a little bit more tedious than the previous two, and the answers are a little bit longer, to take a little bit longer to get, but again, it's just got to find the patterns. A lot of these problems, a lot of these questions across the practice exams are pretty similar, and then having this question down obviously helps, right? But yeah, that's 2019's exam. So yeah, all right, great.